how to scale verification up from the verification of individual functions to larger program units. This paper is about certain aspects that come up when reasoning at function interfaces. So our research is generously funded by the National Science Foundation, so thank you to that great organization for supporting our work. So to start, let me pay homage to really one of the key founders of our area here, that was already, of course, celebrated earlier this week. So Tony Hoare's papers from the late 60s, early 70s really have, of course, inspired all of us. And one of those papers is the one where he introduced Hoare logic, thus really introducing the idea of formal specifications coming together with proof rules to actually do verification of programs. Now that's, of course, that has inspired all of us and has led to great progress and has great mathematical elegance and has been in this sense very influential to us. But of course that's not the only contribution in programming languages that happened in the early 70s. So something else that has affected the world very much over the last 50 years is, of course, the C programming language. Taking somewhat different decisions. So here's Brian Kernighan, who together with Dennis Ritchie and Ken Thompson designed C and used it to write operating systems, and that has really been the foundation of a lot of the infrastructure that we've been profiting from and have been using. So the goal of this verified software toolchain project is really to see how far we have come in the last 40 and 50 years to bring these two areas together and really to develop program logics in the sense of Tony Hoare and in that tradition for the C programming language. So the ST's goal is to have a modern Hoare logic, and by that we mean we should have support for modularity in reasoning, as for example nowadays in the separation logic, which supports modular reasoning concerning heap structures. We want to reason about concurrency, which Tony Hoare of course made fundamental contributions to, and so did Edgar Dijkstra. We want to have soundness proofs of our verifications and the logics with respect to operational semantics. We want to write really expressive specifications where we can really sort of reason about application domains and not only just code correctness. And we have good automation that help the user actually be productive. We want to apply that to modern C. So C itself has evolved in several iterations since the 70s, including additions and refinements of the memory model. Nowadays there are well-executed and well-evaluated formal operational semantics of that available in systems like ComCert, which was another milestone project of our area about 10, 15 years ago. So the first sort of formally verified compiler for C. And C-Lite is indeed one of the early languages in that compiler pipeline. And the ComCert proof asserts that the observational behavior that you can make about a C-Lite program is transferred correctly to an assembly level program. So we would like to bring these two together, and our workhorse, our engine for that is also technology that wasn't quite available in its full glory yet in the 70s, but began to be developed exactly in the mid-70s to modern proof assistants such as Isabelle or, in our case, Coq. They really provide both the mathematical and logical assurance, but also the programmatic features and the expressivity that we think is needed to carry out this project. So we see really Coq as and similarly Isabelle as great integration workbenches for formal methods. And to detail that a little bit more before I go into the technical contributions of this paper, I'd like to outline roughly how BST-based verification looks like. So here we have at the bottom of the slide the ComCert compiler with about 8 intermediate languages here and about 15 transformation phases. You feed in your C code, out comes assembly code. Both languages have deeply embedded syntax, so abstract syntax trees and formal operational semantics inside COC. And there is a soundness proof that asserts the correctness statement that I just mentioned. So in our system in BST, we start just below the entry-level parsing. So at the C-Lite language, our verification works directly on the code representation that ComCert produces inside the proof assistant. So that's in contrast to many other verification tools that define their own infrastructures and then have the task to link their representation to the one that's actually used by the compiler. And that's already a little formal gap that separates statements that they have in the logic from the view of the programming language that's taken then by the compiler. So we write specifications roughly in the style of Hoare. I have a little bit more details on that later on. And then we have the task to construct a proof. This Floyd automation system that is part of the verified software toolchain consists of proof tactics and automation lemmas and so on that help the user to do that, but the process is not fully automatic. So in particular, you need to provide loop invariants in addition to your specifications, and quite often, in particular at the end of a loop, you need to solve entailments between a separation logic formula, and those typically can be simplified using the proof automation, but leave quite often some side conditions that you need to solve then in the proof assistant too. So this Floyd automation system itself is a user-level library that sits on top of the formalized proof rules that we have, and then for which we have formalized soundness proof, and the logic underlying this entire system is quite expressive. So this is the soundness proof as a construction of a deep step-indexed semantics, which allows us to specify concurrency patterns and other patterns of indirection. So this is much more complex than typical formalized soundness proofs for program logics sort of 10, 20 years ago. But it refers directly to the formal operational semantics of C-Lite that comes from ComCert. So again, there is no gap in between these formalisms. So on top of this specification then, we would like to really validate the specifications themselves, again, inside COC. So we want to typically refer in our specifications, for example, to executable programs inside COC's functional language, Galena, that you can independently validate or test or extract. And of course, we are also able to embed other semantic domain models, such as automata models, in our specifications. And we think that is very useful because the top layer really is then the domain-specific reasoning that you typically need to do to convince yourself that the specification that you write down for your C program actually satisfies the semantic properties that you want to do. So we had, for example, a little project a couple of years ago where we looked at building blocks of cryptographic libraries such as deterministic random bit generation, random number generation, and there you really want to validate that the specification of the C program is correct in the sense that you actually have the random number generation properties that the cryptographers think that the construction has. And similar reasoning can be done in any application domain, and it's very useful to have at this intermediate level, for example, executable programs that have a much nicer proof theory than C, so it's much nicer and easier to reason about these domain properties in those using those formalisms than if you wanted to do that directly connected to the C verification. And of course, tying all this together really is the Coq proof assistant. We really want to have all these different components connected to each other so that no reasoning gaps exist, machine checkable proof, but at the same time, by raising the level of abstractions from the lower levels all the way up to the domain reasoning level, it's also sort of auditable by humans. So this particular paper, as I said, concerns modular specification and verification of modular C programs. So here we want to see how much the typical good software engineering principles, in as much as they can be sort of codified as, for example, programming guidelines in C, and principles there sort of can be actually reflected in now the structuring of specifications and proofs. And this is the first step in this direction. So in particular, we have something like data abstraction with representation hiding. For example, if you structure your C development such that you don't include the definitions of concrete structs or heap layout data structures in your header files, but just have abstract pointers to these items in the header file and leave the implementations to the data type implementations to the implementation files. And that enables then really modular program development and code reuse. Now, to reason about this, of course, many people who are familiar with separation logic know about these representation predicates. They showed up already in earlier presentations today, but again, Tony Hoare had a paper on that in the 70s that again laid foundations for those ideas. And similar to the programmatic reuse, we would like to reuse as much as possible specifications and proofs of individual units as we compose programs. So what this talk is particularly about is one aspect there, which is specification subsumption, and the paper also describes another aspect there, which is intersection specification, so just the ability to associate several specifications with a function, which is quite useful, as has already, of course, observed by others, but sort of in a formal system here that again shows up. So how do PSD function specifications look like? So the general form intuitively is a pair of pre and post conditions, P and Q, together with items here abbreviated as Ws that are understood to be universally quantified and allow you to link properties of the state before the execution of a C function to the state afterwards. So here I show another more concrete version of that, which isn't quite sort of the form that we have in Coq, but it's a little bit easier to reason, and I can use that to explain some concrete design decisions that we made. So here we have, in the first line, a typical, what we call this universally quantified list. We also call it with list. That will come up in a second. So here we quantify over various items, and these can be of different types, and these are Coq types. So we can both refer to values of concerts there, so that's val there, but also over items whose type is an arbitrary Coq type. And that is very useful if we want to really relate what happens in a C program to what happens in the domain of the user, the application domain. We then have in the second line essentially our precondition, and in the third line our postcondition. So both contain properties. First talking about the program variables, and then about the heap in the second part. For the program variables, we actually deviate from what sometimes is called Hoare's pun, and that is the conflation of program variables and logical variables. It's actually, in our system, useful to separate these two. So essentially this says, sort of, there is a value x here in purple, which is in the precondition the result of evaluating the program variable underscore x in red, and similar for y. And then the rest of the precondition, the postcondition, will only refer to these values, x and y, but not any longer to the program variables. So the latter part in the precondition then is one of these typical representation predicates that was introduced by John Reynolds and Peter Ahern, popularized. So describing that, for example, the pointer x, pointer value x, then represents a mathematical list of integers sigma 1, and similarly the pointer y holds a list of integers sigma 2, and then this is a specification for the append program. In the post condition, we see then that maybe there's a return value that points to the result of appending these two lists. And again, the use of operators from the ambient logic again allows us to connect reasoning about C with reasoning about the application domain, in this case lists. And I'm hiding here and not being specific, for example, whether the sigma 1 and sigma 2 are actually unsigned ints or signed ints, or indeed they could be here just idealized integers from the mathematical domain Z. All these differences would come in the definition of a particular list segment predicate. And just for completeness, this is how this specification looks like in our actual tool. So there's a little bit more notational overhead, but the structure is really similar to this. So let me now briefly say what motivates this subsumption, which we write as with a less than colon equal, relating a specification phi on the left and psi on the right, and it is following the principles that was developed in type theory, where you also have a notion of subsumption, typically involving expressions with different types here, sigma and tau, and they allow you to prove that an expression has type sigma, but then use it at various places as if it has type tau, providing this subsumption relation holds. And that's something quite useful for us also when looking at function specifications. So we would want to verify, for example, a body of a function with respect to one specification, and then at function call sites use it with a slightly different specification. Because when we write the initial specification, we may not be able to predict all the use cases that we have. So in the paper, we outline several examples of that. We have a running example of piles, but representation hiding, where, for example, in phi, you say more about the internal layout of the data structure than you want to expose to different clients, as one example. So quite often, actually, you want to provide different interfaces of a compilation unit to different clients. So that's another use case of this subsumption. We have examples in the paper, again, where it's useful that in addition to the regular frame rule of separation logic, we benefit from also having framing inside this subsumption rule, and we've observed that sometimes functions actually have redundant parameters and arguments that can also be nicely treated here. So for the question is then how one can define such a relation, and I'm not going to show the full formal definition, but just see how it extends work that was actually done 10, 15 years ago already. So if you started naively from Hoare's rule of consequence and thought, okay, we have preconditions and postconditions, both for statements but also for functions, then that gives a good intuition already. Now you would then have to say, okay, where do we want to reason about this at the level just inside the function definition, so inside the body, or at the call sites? But there are actually a couple of other questions that come up and that make this view a little bit restrictive. So, for example, here the implication between the two postconditions needs to hold no matter whether the precondition was satisfied, so you cannot exploit knowledge that you have inside the preconditions so easily here. Another issue that was actually already observed in the 80s was this issue of parameter adaptation. So in practical situations, the types of these with lists W that I had on an earlier slide here, they may actually be quite different in the two specifications involved in a subsumption. And so Thomas Kleiman sorted this out for a toy language about 20 years ago, but now that we have another 15 years of program logic and separation logic, there are additional complications that come up here that he did not have to consider. And the existence of function pointers is one. The expressivity of our logic is another aspect. Kleiman could explicitly quantify over states here for all sigma. So here, our logic, because it has this complicated step indexing model, doesn't give us directly access to these quantifiers, so instead we need to use entailments. And because we are step indexed, actually our definition will also have modal operators there. But nevertheless, our definition of subsumption, and even this is only a slight simplification, follows structurally really from similar principles that Thomas Kleiman had. So the precondition of the more abstract specification should then entail the existence of a witness for the more concrete specification. In our case, it should also or it may also imply the existence of a frame, and with that, then you have to establish the precondition of the inner specification, of the more concrete specification, and then similarly the opposite entailment at the end. So this is structurally similar, but looks now a little bit more complex. So in the paper, as I mentioned, we have a worked example that has several aspects of code reuse and specification reuse and motivates these conditions. We note that the usefulness of framing was just 1 or 2 years ago also observed by Bart Jacobs in his very fast tool. So I talked to him in May and found that out. The paper also describes these intersection specifications, and again we're really inspired here by the insight that people in type theory have had. So the rules relating our sets of specifications follow exactly the same rules and that you expect. In particular, also they interact with the subsumption in the same way as they do in type theory. And in particular, we have then also proof rules for pointers. So let me conclude. In VST, we really aim to combine meta-theoretic reasoning about the program logic, so soundness and the like, with practical program verification and connect to domain level reasoning. We're now at a stage where we can really explore how much we can really support practical modern software principles in the structuring of specifications and verification. One aspect that we think will still be useful there is again another item from type theory, which is formal existential quantification to model representation hiding. But because we're working in this expressive logic of COC, we don't have to redefine all these logic principles, but we can really exploit all the work that has gone into the design in this system. And yeah, we'll explore that further for component calculi and subclasses with behavioral subtyping and so in the next few years or so. Okay, thank you very much.